Hello, my name is Joseph Seiss, University of Connecticut. I'm doing a presentation on the dissolving of cellulose for the production of ethanol for Dr. Cooper's Engineering 1166 class. My presentation is based on the AiChe journal article, The Complete Dissolution and Hydrolysis of Wood in Hot Water by Zhen Feng and Chun Feng, part of the biomass group of the Chinese Academy of Sciences. In this presentation, I will talk about ethanol as a renewable fuel, cellulose, what it's made of, how to get sugars from cellulose, supercritical water and how it's used, using water to dissolve cellulose, the goals of engineers, engineering solutions in dissolving cellulose, and using sodium carbonate solution to dissolve cellulose. Ethanol is the most widely used renewable fuel. 13 billion gallons of ethanol are produced worldwide, and the U.S. consumes over 9 billion gallons annually. Ethanol is made from the fermentation of simple sugars such as glucose. Ethanol is most commonly produced from corn. Research has shown that production of ethanol using corn yields 34% more energy than it takes to produce it. Using corn is raising food costs and creating food shortages in many countries. Steps are being taken to create an efficient method to produce ethanol from cellulose, which has a higher energy yield and will not impact food supplies. About 33% of all plant matter is cellulose, which makes it a very reliable and abundant source of ethanol. Cellulose is found in the cell walls of plant cells. It consists of long chains of polysaccharides held together by hydrogen bonding to form rigid walls that are hydrophilic. It contains three main components. Cellulose, which is a polysaccharide composed of long chains of glucose. Hemicellulose, which is composed of several different sugars, such as glucose, galactose, and ribose. And lignin, which gives the cell walls added strength by bonding with hemicellulose, and it consists of three different alcohol groups. In order to separate cellulose and other polysaccharides into simple sugars, a water molecule must be added to the chain to break the bonds holding the sugars together. This is called hydrolysis. Enzymes are currently used to aid in the hydrolysis of cellulose. This process of using enzymes is expensive and cannot continuously produce large quantities of simple sugars. Engineers are creating methods for the fast and efficient breakdown of cellulose using supercritical water and alkaline salts. As water is heated towards its critical point at 374 degrees Celsius and 22.1 megapascals, at the point indicated on the phase diagram of water, 70% of its hydrogen bonds are destroyed, and water molecules lose their dipole moments. With no dipole moments, supercritical water is able to dissolve many apolar organic molecules, including cellulose. Water molecules also dissociate into hydrogen and hydroxide ions, producing a water equilibrium constant 132 times greater than that of normal water. This high concentration of hydrogen and hydroxide ions can hydrolyze many compounds without the addition of an acid or base, and most importantly, can induce the hydrolysis of cellulose. In order to dissolve a mixture of biomass or plant products containing 50% cellulose, 25% hemicellulose, and 20% lignin, the mixture must be quickly heated at a rate of about 10 degrees Celsius per second to the critical point of water. At 320 degrees Celsius, the complete dissolution of cellulose is observed. The problem with this process was that only 40 to 60% of the biomass was dissolved, leaving behind a solid residue that would cause a blockage in flow reactors. The goal of engineers is to create a process that completely dissolves biomass into a homogeneous mixture and hydrolyze cellulose for the production of ethanol, while at the same time avoiding the decomposition of molecules into a solid residue. The best way to completely put biomass into solution is to dissolve it into a solution containing an alkali salt and heat it to critical point. 9 alkaline catalysts were tested, including calcium carbonate, calcium hydroxide, sodium carbonate, sodium hydroxide, sodium formate, potassium hydroxide, potassium carbonate, sodium chloride, and potassium formate at 300 degrees Celsius to see which one is most effective for the liquefaction of biomass. Experimentation showed that a 0.8 weight percent sodium carbonate solution was the best catalyst for dissolving biomass. Sodium carbonate helps dissolve cellulose by first reacting with carbon monoxide to start a chemical reaction pathway including 4 separate chemical reactions. Equations 2 and 3 show the decarboxylation of the biomass from an ester reacting with the formate ion HCOONA formed in equation 1. The formate ion is then regenerated in equation 4 and the reaction starts over. When a biomass sample was added to a 0.8 weight percent sodium carbonate solution and heated at a rate of 9 degrees Celsius per second, all 3 components simultaneously dissolved at 329 degrees Celsius, and the hydrolysis of cellulose to glucose occurred. A sugar solution was formed upon cooling, and no solid residue was formed. Because no solid residue is formed, the sugar solution can be produced continuously in a flow reactor, and upon cooling, used in the production of ethanol. In conclusion, 0.8 weight percent sodium carbonate solution can dissolve cellulose upon rapid heating at about 10 degrees Celsius per second. All components of biomass dissolved at 329 degrees Celsius and no solid residue is formed. The sugar solution can be used in the production of ethanol. Thank you for watching, and here are a list of the sources that I used.